Future advances in hyperspectral imagery promise to be a major benefit for mineral exploration. Remote sensing technology is advancing rapidly, but still only a handful of satellites are available with the technical quality, ground resolution, and spectral range that geologists demand for mineral exploration or mining purposes. In this presentation, I'm going to explain the benefits for the mining industry using Earth observation sensors, how it is done, and discuss a few platforms these observations are made from. Mineral exploration aims to discover deposits of minerals and rocks that can be used to meet society's resource needs. The exploration includes the search for commercial raw materials such as clay, limestones and sulfurs, ores for which metal can be extracted like iron, copper and zinc, and gemstones such as diamonds, sapphires and opals. Solid fuels are a very major part of mineral exploration, as coal, oil shale, and even uranium is mined to produce electricity. Mineral exploration entails a wide range of activities, from prospecting for new mineral deposits to the feasibility study of economic mining. Throughout history, various exploration techniques have been used, from panning for gold to reference usage of complex spectral libraries. During the early 20th century, aerial photography was extensively used and rapidly evolved as new uses was discovered and new methods were improved. During these times, aerial photographs was used as aerial surveys to map roads and rivers, fences and other objects that would delay the preparation of mining. Thus it was more often used for prospecting. Mosaics were made by joining a number of vertical photographs or parts of photographs which have been reduced to a common scale. This arrangement of photographs made it possible to study the configuration of the ground with immense detail. However, there were not sufficient methods to reduce or eliminate distortion in the 1930s. During these times, aerial surveys were severely limited to cost as the technology of cameras and flight plans were in their infancy when it came to reliability. Remote sensing improved throughout the mid-1900s, yet still lacked the ability to map specific clay or iron minerals that are key to discovering new minerals and hydrocarbon resources. After World War II, satellites started to be equipped with radar and infrared cameras. This was a major improvement to the conventional aerial photography because of the ability to see through cloud cover and enable users to spot camouflage. By efforts of the geologists of the United States Geological Survey (USGS) and NASA, various Landsat satellites were sent up that have been continuously collecting data for nearly 50 years. Today, mining companies employ specialized companies to analyze spectral data from these satellites. In December 1999, the Terra satellite was launched. One of the 5 sensors on board is the well-known ASTER satellite sensor, Advanced Spaceborne Thermal Emission and Reflection Radiometer. This sensor measures reflected and emitted electromagnetic radiation from Earth's surface and atmosphere in 14 bands. There are 3 groups of bands. 3 bands record visible and near-infrared radiation reflectance, 6 record shortwave infrared reflectance, and 5 record emitted infrared or thermal infrared at a resolution of 90 meters. This wide variety of shortwave infrared makes it possible to identify minerals and mineral groups such as clays, carbonates, silica, iron oxides, and other silicates. These minerals groups can be detected using image enhancement methods. For example, in order to detect quartz, thermal infrared bands are used as are used as quartz minerals exhibit strong vibrational absorption within 8 and 14 micrometers. This image on the right displays thermal infrared bands 13, 12, and 10 as red, green, and blue. In, in this wavelength region, variation in quartz content appear as more or less red. Carbonate rocks are green and mafic volcanic rocks are purple. The two images on the left are taken of a copper mine in Chile. The middle image displays short-wave infrared bands 4, 6, and 8 as red, green, and blue. In this wavelength region, clay, carbonate, and sulfate minerals have diagnostic absorption features, resulting in distinct colors on the image. For example, limestone are yellow-green, and purple areas are kaolinite-rich. ASTER data comes pre-processed radiometrically and geometrically, but there are still a few things one needs to consider when working with ASTER data. Firstly, cloud cover, vegetation, and atmospheric effects can severely mask or alter surface signals. Secondly, bands and band ratios do not indicate the occurrence or quantity of a mineral with absolute certainty. As a result of these factors, it is important not to examine ASTER images in isolation from other data. It is therefore recommended to use radiometrics or other datasets in conjunction with ASTER for best results. Compared to older remote sensing sensors like the thematic mapper from the Landsat program or previously mentioned ASTER sensor, WorldView 3 has a major increase in radiometric, spatial, and spectral resolution, and a greater potential in applications of remote sensing. The satellite has an average revisit time of less than 1 day, making it capable of collecting up to 680,000 square kilometers of imagery per day. The satellite was developed by Digital Globe, now Maxar Technologies, and launched in 2014. This satellite is a multispectral commercial satellite with the highest spatial resolution currently on the market. Its single panchromatic spectral band is used to rapidly collect high-resolution imagery of 31 centimeters, which is particularly useful for capturing sharp image detail. The visible and near-infrared system collects 8 1.2-meter resolution multispectral bands, primarily used for searching iron minerals and rare earth elements. In addition, the WorldView 3 had 8 shortwave infrared systems that the WorldView 2 lacked. These shortwave infrared bands have a pixel resolution of 3.7 meters and is used for the measurement and mapping of clay minerals. Lastly, WorldView 3 featured atmospheric sensors known as CAVs with an additional 12 spectral bands. CAVs bands provide very accurate atmospheric corrections in imagery for the effects of clouds, aerosol, vapor, ice, and snow, hence the name. Here on the left is an example of atmospheric compensation. Digital Globe created an algorithm that removes haze and vapor particles and is used to correct and clarify high-resolution panchromatic and multispectral satellite images under diverse atmospheric conditions. The increase in shortwave infrared bands compared to that of the ASTER made it superior in many applications, such as disaster evaluation, surveying of geology and mineral resources, exploration of petroleum and geothermal resources, and non-renewable resources evaluation.